We have developed at MIT reactors on the scale of 20 kilograms per day. We have developed them, however, with what we call synthetic materials. That is to say, we mimic the composition of industrial streams or geological minerals, and we are processing these currently in my laboratory to establish the process parameters and narrow down the cost and the operational window for the process. So we have reached that stage now, but of course every mine, every stream, and sometimes every metal has its own specificity that needs to be tackled. That is the reason why today we are reaching out to industrial players, to certain regions in the world, in order to work with them to demonstrate and evaluate how the technology we have developed can apply to the actual resources, actual materials that companies are handling, mining, exporting, or generating in their processes. We are actively seeking partners to run our reactors and our process with their material. We have developed the entire suite of tools to evaluate the scalability, the cost, and the feasibility at the scale that each plant or each company is interested in. But now is the time to basically go for it and try with the actual materials in our laboratory. And in that sense, we are actively seeking companies that have the vision of this future and new sustainable processes, as well as the actual need currently to do things with these streams that are considered unconventional or sometimes too difficult to process economically. And that's a particularly exciting time for us because we are engaging with major partners, major corporations, to define the future of the field for a more sustainable and more efficient materials processing and extraction technologies. On the way to developing this integrated new way to extract copper and nickel and other metals, we have actually developed a step, so like a small version of a process. We call that a unit operation, which is able to selectively convert a valuable metal, let's say a copper at low concentration in minerals that typically we don't mine or we don't process because there's not enough copper, or the copper is in a chemical form or a size that is not suitable for existing mining and minerals processes. Well, for that specific situation, we have developed a new reactor, a new technology, which enables to form a new chemical phase for the valuable element, and it's able to form a larger, a bigger phase for the valuable metal that we are referring to. And by doing that in a solid state manner, so imagine a rock that you break down in a reasonable size, then you expose that to the process that I'm referring to, and that enables to nucleate and grow certain phases of the valuable metals that you are after. By doing this in a very cost-effective way and in a fast way, we can then take this existing rock or stream or whatever materials we processed, and we can now use very conventional, very simple physical separation technologies to recover the valuable metal. The type of physical separation that I'm talking about can be density separation. the new metal that we form is in a new phase that is heavier or lighter than the rest of the solids, and therefore you can use water or any medium to basically float or sink the valuable metals of interest. Other minerals technology that we enable are magnetic separation. The new phase that we have formed, because the particles are bigger, because they are a different chemical phase, can actually react to a magnetic field, and that helps you to use a magnet to basically pull away the particles of the valuable metal that we have produced. This is particularly exciting for us because this specific reactor, this specific unit operation, could be translated very soon. Within 2 years, we could deploy that in an existing minerals processing plant. This is a little bit different than the electrification that I talked about before, where the electrification requires cheap electricity to be available and is kind of a 5 to 10 years or horizon development. This specific unit operation process could be deployed as early as 2 years from now, because it scales and it's based on very well-known reactor technologies that are available currently on the market. So in that sense, we are much closer to a very short-term deployment of the finding we had in our lab and the ideas we developed and the reactor we developed. And that's particularly exciting for us, again, in the context of collaboration with industries. We are now ready to accept 20 kilogram, 50 kilogram, 100 kilogram of materials that we think is amenable to the unit operation that we have developed, and we can then send them back and they can be further tested or further tried in an industrial plant. And for us, this is particularly important because it's the outcome of 5-7 years of intensive lab work with a lot of exchange with players from all around the world to inspire and think about how can we develop a very practical approach that is transferable to the industry soon. And I think that's what's driving us currently is the pressure of having our technology impact the outside world, and in our case the world of minerals and metals processing, makes us very eager to provide quickly scalable processes that can be transferred sooner to the existing operation, as opposed to waiting for a complete greenfield and complete revamping of an entire sector.